So we're getting into pulling all these different variables together now, and we're going to talk about planetary circulations. What are we world are we, why do we want to talk about something that covers the globe? Well, what we're looking for here is patterns that should be normal. These are things that should be happening every day, some way or another. And then the weather that we experience kind of flows out of these patterns. Uh, so as a whole, if you averaged everything together in winter months over the last 20, 30, 50 years, or if you averaged everything together over the summer months or the spring or the fall, these are patterns that emerge. Why they emerge? They emerge because we've already learned that how energy is distributed on the globe is one way, and how the interaction of the moisture with that and the interaction of pressure with that, all these patterns flow out of that. Now, yes, there are smaller scales that contribute when a low pressure comes through your area and causes rain, or thunderstorms develop over your house, or hurricanes develop in the tropics. These are on a smaller scale, scales we're going to learn about. But right now, we're going to look at a global scale, a really large scale. But with that in mind, first off, let's think about the Earth. If it didn't rotate, we'd have one side that's always dark and one side that's always sunny. Right at the equator would be extremely hot. And so that would cause the air to rise because that would be the hottest area. On the far side, away from the sun, would be the coldest. So all you would get is a giant circulation in the northern hemisphere and a giant one in the southern hemisphere. No rotation, no change of how the Earth orients itself to the sun, all of that. Very simple. And we have planets in the solar system that are actually like this. For example, Mercury has one side always in the sun and one side always away from the sun. So, kind of interesting how that shapes their weather. But we have rotation. So, what happens when that happens, the rotation? We wind up with three belts in the atmosphere. Notice that down here below 30 degrees north, we have the easterlies. Everything's coming out of the east. And the same kind of happens in this down here in the south of the equator. Now, our latitude, everything comes out of the west generally, right? So we're in the westerlies. We talk about that. And then north of that, we have more easterlies, low pressure rotating around surface, high pressure at the surface, but low pressure aloft at the North Pole. So think about it. If I have air converging here, if I have converging air at the surface, I'm going to get rising air. I'm going to generate low pressure in this area. Here we have air moving across, away from each other, pulling air down, sinking, clearing. Nice sunny weather, high pressure. Along the equator, the air comes together, and what do we get? We get the low pressure again. So if you look at a globe, look at the weather maps, you would generally see high pressure around 30 degrees north, low pressure 60 degrees north, and another area of low pressure along the equator. And these are going to follow the sun. In other words, as the sun moves north in the summertime in our area, instead of at 0 degrees, this low pressure is going to move upwards towards 23.5 degrees, maybe. The same will happen in the winter. Everything will shift southward. So let's look at some of that. Here you see the high pressure and the low pressure, just like we just talked about. All of this is coming out of things you've already learned about the wind and the pressure. And here is our semi-permanent pressure pattern. We have typically in January a strong low pressure over Greenland, across Alaska and stuff. And then we have this high pressure right around 30 degrees or a little south of 30 degrees. It's a Bermuda high, if you think about it. If you ever heard the Bermuda high term, there's a big high pressure there. And in the summertime, notice how it's moved north. If you live along the East Coast this past week, you were influenced by the Bermuda high. The Bermuda High has been sitting off the east coast of the United States, pulling southeast winds into the southern half of the east coast and up along the coast and then moving back out to sea further north. That has blocked any high pressure systems or lows coming in from the north into that area. So all we've done is just generate a continual flow of air coming out of the tropics across the eastern US and then back out over the Atlantic. So with that, we can talk about these anticyclones that form at around 30 degrees north. Lots of warming, but interestingly, look at this part here. On the eastern sides, we have a lot of sinking. So warming occurs on the eastern side of these highs. Low relative humidity, mainly fair skies. And oh yes, the Sahara Desert would be there. Uh, there's a desert over Chile. Almost all deserts on the earth are on the eastern side of these highs. Western side, where we typically live in the eastern United States, on the western side, the southeast United States particularly, what do you get? Lots of rain, especially in the summertime. Now you go up to the north and you get these subpolar lows that track across. And they're typically right along a frontal boundary. We have cold air to the north, warmer air to the south. And then atop, there's a big cold anticyclone that literally develops right over the North Pole or the South Pole. Above that, we have the polar vortex. That is because the air is so cold up there, we know pressure drops fast in cold air. So what it does, it drops so quickly that it forms a low pressure system aloft in these areas on the northern hemisphere, in the North Pole or South Pole. So you wind up with a big, strong, low pressure system sitting over top the poles. Now, in between, we have a nice, simple westerly flow over us. Notice it oscillates, goes up and down with ridges and highs. We're going to talk a lot more about that the next. All right, so we've talked about the tropopause being highest down near the equator and lowest up near the poles. Well, if you think about it, air almost always very cold north of 60 degrees north. So the tropopause pretty uniform, very low. Same thing down towards the equator, pushes it well up. In between where we live, where fronts occur, this tropopause can go up and down, particularly following with a cold front or a warm front with low pressure. So it's interesting the fact that the tropopause is higher down here by the equator and lower up here by the North Pole. And in between, it oscillates. Now, to the south, we call the trade winds. The winds that, if you ever go back and study Columbus's voyage to the United States, he tried to get into the trade winds. And back then, when they had the sailing ships, they knew the winds blew from the west, from the east to the west across that area. So along that trade wind route, just to the south side of that big high pressure, you can move pretty steadily, typically have fairly decent weather. And with that, underneath, below this substance coming, sinking air coming down, was a layer of ocean and a marine layer on the bottom of it. So you wind up with a warm layer above it, well mixed, and then a cool, humid, stable air on the bottom. It forms a inversion. A lot of islands really are what you're talking about. Think about Hawaii. Hawaii sits in the middle of the trade winds. You would think, oh, Hawaii, all this warm water, lots of sunshine. Man, they're going to have all kinds of thunderstorms there. Well, they don't. The reason is the trade winds have created an inversion there. So yes, you'll get these cumulus clouds developing. They hit the trade wind inversion and they flatten out. They don't get high enough to make thunder. They can make rain, but they can't make thunder. Now we talked about right along the equator being the intertropical convergence zone, or low pressure. Notice January, it sits down right here, just a little bit south of the equator. Summertime, it moves north. What I want you to notice is how much it moves over land. Why does it move over land so much? Well, land heats very easily. Oceans don't. We know the specific heat of an ocean is really, really high. It takes a lot of sun's energy to heat the ocean, whereas land, not so much. So what happens is it gets hotter over the land. And when it does that, this intertropical convergence zone has moved north. So if you were to sit here in India in January, you would have big high pressure sitting up here in Siberia and winds coming out of the north, coming across India all winter long. At some point, this intertropical convergence zone is going to move north of India in the spring, early summer. All of a sudden, the winds are coming out of the Indian Ocean. The Indian Ocean is fairly warm. So what happens is you get all this moisture, warmth coming up, tremendous rain occurs. And because this intertropical convergence zone moves either north of them or south of them, we get a steady wind. That's the monsoon wind that lasts for a long time. And here you can see it. Look at how that monsoon came in, and we wind up with the Arabian Sea, Bay of Bengal, all of that area, pulling in moisture, very wet in a lot of parts of Asia in the summertime. We also talked about how highs move north or south. Well, in the wintertime, the high is pushed south of San Diego. If it is pushed south of San Diego in the wintertime, it allows some of the jet stream to the north to bring the low pressures and stuff that come across further north, typically in the summer, further south. You get a little bit of rain in San Diego in the wintertime. In the summertime, that same high has built back to the north, so they get almost no rain. Now, they're on the west side of that high, the big high at 30 degrees north. Actually, they're on the east side. I'm sorry. And then on the west side is Charleston. We saw how the moisture can flow around that big high that I was showing you going on there. Right now, in the past week, lots of rain in Charleston, South Carolina in the summertime, less in the winter. Because of these semi-permanent features in the atmosphere, they actually influence ocean. They create big circulations in the ocean. You look at the Gulf Stream that comes out of the Gulf of America or Mexico here, and it moves up along the East Coast. Well, what happens is this North Atlantic gyre, the big 30 degrees north high pressure, has created a circulation in the ocean, pulls the ocean flow up along the East Coast and out towards England, eastern parts, western parts of Europe here. By doing that, it actually pulls warmer, moist water up there, moderates the climate, all because of that high sitting down here. Monsoons. This is the North American monsoon. I know you've read about the flooding out in the West that's been going on. Uh, Part of that maybe contributed some to this monsoon, part of it to some other aspects. But what happens is there's a mountain range down here in Mexico. That mountain range heats up. It's high, it's dry. It really heats up early in the summer or even into the early spring. When that happens, it allows air to rise. Your air is warmed. You form low pressure at the surface. Aloft, you form high pressure. That low pressure is pulling in moisture. Think about it as a big, giant circulation. It pulls in air coming off the Gulf and off the Southeast Atlantic, Pacific, all into that area. Very hot, very humid. What you wind up with is a lot of showers and thunderstorms this time of year. The more powerful it is, the more thunderstorms and rain you get. This is also probably what helped to contribute some of the moisture here, because it occurs in Arizona, New Mexico, and western Texas. So it may have contributed some of the moisture that occurred in this area as well, where the flooding occurred. And in Mexico, New Mexico has been having flooding, which was contributed to this as well. Rossby waves. All right. Rossby waves, you saw there's an oscillation at 500 millibars in the wave pattern. Well, if you were to look at it, you would see small waves rounding through bigger waves. In other words, you would have like a big trough of low pressure over maybe 40 degrees longitude. And in it, you might have these little 10-degree longitude, little wavy patterns. The big waves are the Rossby waves. The little ones are the short waves that cause a lot of the weather. There's also a zonal flow and a meridional flow. Zonal flow, typical many times of the year, you wind up very fast west to east flow, just little undulations. So yes, cold air is getting pulled down here, warm air is getting pulled up here. However, when you get to meridional flow, much deeper, goes much further down, it creates much greater temperature contrast. This is going to cause much stronger low pressures, much stronger highs, so that you wind up with, oh, when that low moves by, you get a very strong shot of cold air, or maybe ahead of the low, you're going to get a very warm air mass in the wintertime. And then there's the blocking patterns. If you've ever watched a stream, put a rock in it, you'll see circulations that just kind of develop around that rock, making just a circle. They're not really letting the water go through on around that one side of the rock. Interestingly, there's a lazy river in water country here near me, which I used to love to ride. And as part of that, there's an island in the middle of that river. If you hit that area in a certain direction, you literally will find up this blocking pattern. You'll just circle around right in one part, never moving along the river at all. And you can get bumped a lot that way. So you got to try to work your way out of that area. So with these blocking patterns, sometimes they set up and they cause tremendous amounts of precipitation or very dry weather for a very long time. And you can see here that worked March to May of 2019, very dry weather along the east, very, very wet, moist in the central part of the United States. All right, jet streams. Jet streams are where the air moves the fastest. They're typically between 200 and 300 millibars. They're going to be higher in the summer and lower in the winter. They're going to be stronger in the winter because they're greater temperature contrast. Why do they form? All right, you all learned, hopefully a little bit, that as the air gets very cold, pressure drops very quickly. As the air gets warm, pressure drops slower. If I have a front down here, what happens on the cold side of that front, pressure is dropping very fast. On the warm side of that front, pressure is not dropping. So you're creating a tremendous pressure gradient across here. Further up you get in the atmosphere, the stronger that pressure gradient gets. So that is where the jet stream occurs. Pretty much very close to the tropopause. So, and here are the seasonal shifts. You'll see the summer jet stream up north, winter jet stream pretty much down to the south. And I talked about these little short waves that propagate through the jet stream and through these Rossby waves. Here's a Rossby wave. Here's the little short wave. Because of that, they create divergence aloft, which allows low pressure to develop at the surface, and convergence aloft, which allows high pressure to develop down at the surface. So actually the upper level jet influences the surface weather pattern. In that jet, what we call jet streaks. And as part of that, you'll notice if you were looking straight ahead along the jet streak, on the left front side, you'd see a D for divergence. On the right rear, you have divergence. These are areas where low pressure has a tendency to develop. convergence, where high pressure has a tendency. All right, there's other aspects. When you look at the globe as a whole, because this is a fluid, if I do something in one part of the globe, that means that that fluid may react in a different way in a different part of the globe. El Nino and La Nina are that kind of impact. El Nino means that the temperature is warmed in the Pacific, and because of that, it changes the weather pattern over the United States and even into Europe. La Nina means the temperatures have gotten cooler over the Pacific, especially we're talking mainly ocean temperatures here. They influence. If I have a warm ocean, I wind up with a lot more thunderstorms, weaken the trade winds out there, and that changes the rest of the weather pattern around the globe. If I have a cold ocean, we get stronger trade winds, less thunderstorms. And here you can see the history of that. All right, one other little aspect we're talking about here is the Ekman spiral. Have any of you ever visited the Outer Banks? If you go to Hatteras or parts of the Outer Banks, this is notorious for occurring. What it is, if I have a southerly wind along the eastern United States, which if I keep a Bermuda high out there long enough, I'm going to get, I'm helping to pull the water right up along the East Coast, creating a current stronger than normal near the coast. Because of that, the Coriolis effect begins to work on it, pulls the water to the right. Well, the top layer of the water begins, the lower down you go, the more and more to the right. That water is going to turn until you finally literally make a curve, an Ekman spiral. But what that does, it pushes the water down here way low up to the surface. So you wind up with temperatures cooling dramatically. There have been cases, and I had friends that got caught in this. One day, temperature off of Hatteras was in the mid 80s. The next day, it was in the mid 50s, all because of this kind of output. We talked about a little bit about the warm phase and cold phase of El Nino here, and you can see here's the thunderstorms developing during El Nino, slowing the jet stream. So, and these have significant impacts around the globe. There's other parameters. North Atlantic oscillation is one. If you have a positive index, and these North Atlantic oscillations can last for weeks at a time, and they can really influence our winter. You can see here colder than normal on positive North Atlantic oscillations, warmer than normal on negative ones. Arctic oscillations. Think about this. If you have a very strong low pressure system aloft over the North Pole, the air is blowing very hard. Oh, all of a sudden that air is flowing less, not as flowing as strongly around in a circle. It begins to allow some of that Arctic air out from over the poles. That Arctic air comes down in the United States. It's all we're talking about with an Arctic oscillation, where it's very, very intense. Arctic air stays over the poles. We don't get any in the United States. Milder winter. If it stays a little bit weaker, we get more Arctic air coming down into the United States. We can have a pretty cold winter. There's a Pacific decadal oscillation as well, which just another long-term phase that we will look at. All right, Magellan-Julian oscillation. They have discovered the last 40 or so years, thunderstorm clusters develop in the tropics, particularly in the Indian Ocean or western parts of the Pacific. They get a very intense area of thunderstorms that develop. Big, we're talking, 400 or 500 miles across of thunderstorms. And that gradually moves across the globe. It can take 30 to 60 days to get all the way around the globe. But as it's moving, that up and down motion it has generated out there moves across, and it can help influence hurricanes. It can influence low pressure systems. It can make high pressure systems. So we track where, once they've developed, how they move around the globe and see the impacts they actually have. So with that, wanted to show you just a couple things that are going on right now. All right, we talked about the high pressure. Here's the high pressure out over this area. It's been sitting here pushing in warmth, moist air. Look at where the lows are. All the way up north here, around 60 or more degrees north, there's different low pressures. So matches up pretty well with what we were talking about as this type of pattern for the globe. And I wanted to look at the jet stream. So we'll take a look here at 300 winds. And let's go 250. And we'll take a look at it. Notice very strong winds just south of Alaska. They're up around 50, 60 degrees north. They come in here, northern part of the United States, dip back up and go on out. If I was looking for a Rossby wave in this pattern, I'd argue it's somewhere in here because there's low pressure here coming up. But notice how they don't go very far south either this time of year. They're definitely staying to the north. Pretty strong though, 100 and some knots out here. What you'll see in the fall is these will begin to move south and it'll begin to impact our area. Final thing I wanted to show you on quickly through climate, global patterns. We can take that and make estimates on how they're going to change, and even on the drought, like that monitor there and all. You'll notice there's plenty of drought in some areas in the West still, even though there's significant improvement in some. And this is what's currently going on with El Nino. And right now, you see in the wintertime, we had La Nina going for a long time here. Temperatures around about a degree below normal for much of the winter. Now, pretty much neutral. So that's why we're in a neutral phase of El Nino for the time being. So I know I've talked a little bit, but the global circulation is very important to have an understanding. So let me know about any questions you might